So far today, we've only talked about indefinite integrals, plain old antiderivatives. So now we're going to look at some definite integrals and see how it's a little bit different. So let's take a look at the first one. The definite integral from 0 to the square root of pi of x times the sine of x squared dx. And hopefully your first thought is, wait a minute, this one can use u substitution. This one has exactly what I keep mentioning. The derivative of the inside function is sitting right here, ready to be taken out. Sure, we're missing a 2, right? The derivative of x squared is 2x dx. So we're going to need a 2 there, but that's okay. We can put a 2 there as long as we put a 1/2 there also. And so we'll use u substitution. We'll set that up. U equals our inside function. And I apologize that we use u for u substitution, and we also use the letter u in integration by parts. Sorry, not much I can do about that. The du is 2x dx. Hopefully you're remembering, wait a minute, when we had definite integrals with u substitution, we had to do something with the limits of integration also, and we are going to do that now too. I cannot write the definite integral from 0 to the square root of pi of the sine of u du. I can't do it. Or I could, but it would mean something different from what my problem started with. Because these limits of integration are x values. But if I'm about to take a derivative in respect to u, I can only apply u values to them. And I could just take the antiderivative of x sine of x squared dx, keep the antiderivative, put it back in terms of x, and then apply the limits of integration. But there's an easier way. I'm going to make new limits of integration, say that if u is x squared and I want my limits of integration to be in terms of u, well, I'm going to take my old limit of integration, lower limit of integration, and apply it to my u. Well, 0 squared is still 0, and the square root of pi squared is equal to pi. So what I can do is rewrite my limits of integration as 0 and pi. So we want the 1/2 times the definite integral of 0 to pi. The sine of x squared, I'm going to write that as the sine of u, because I took out the x squared and replaced it with u. And the 2x dx, which was in my integral a minute ago, in my integrand a minute ago, well, that is my du. So I'm going to replace the 2x dx with du. And what's cool is since I replaced my a and my b in terms of x with a new a and a new b as values of u, I don't even have to write this here, but these are u values, which means I don't need to go back to x's at all. I can just take the antiderivative of the sine of u, which is negative cosine of u, and evaluate that from u equals 0 to u equals pi. So that's 1/2 times the negative cosine of pi, which is going to be negative 1. Fix that in a second. Minus the negative cosine of 0. So I have 1/2 negative 1 plus 1. So that's 2/2, which is equal to 1. Easy as pie. Maybe. For my other example, the definite integral from 2 to 4 of x times the ln of x in respect to x. This one's a little bit different. I'm looking for u sub first because I'm always looking for u sub first, but the derivative of the inside is not what I see on the outside. I can't just fix it with a coefficient or 2. The derivative of x is plain old 1. I've got an extra x on the outside there. I can't get rid of it with u substitution. It's not going to work. What we can do instead is set up the u substitution that we've been doing today. But our approach to direct integration, when there is a integration by parts problem we need to take care of, is going to be different from what we did with the u substitution. I'm not going, and there's more than one way to do this, so I'll show you more than one way. But the way I recommend doing most of the time is by first finding the antiderivative, the indefinite integral of x ln of x dx. So I have to write that that's what I'm doing. I can't just start working on it, because this is a different problem. This isn't what the question asked me to do. I'm always allowed to do more math on the side here. But if I'm doing something that's not what the problem asked, I have to say that's what I'm doing. So I'm going to find the indefinite integral of x times the ln of x in respect to x first. And that will require some use of some integration by parts. So I've got to decide which one of those factors is going to be my u, which one can differentiate easily and get a little bit simpler, and which one is going to be my dv, something that I can take the antiderivative of. Now, I do now know what the antiderivative of ln of x is, but it's not any simpler. So we're going to want to avoid that one if we can. And what we can do instead is say that u can be the ln of x, and dv can be x dx. I know normally when we see an x out there, we think, oh, that's going to differentiate easily. We'll make that be our u. But in this case, that wouldn't help us. What we'll do instead is try to take the derivative of ln of x is 1 over x dx. And the antiderivative of dv is x squared over 2. And so now we can apply that to our antiderivative. The antiderivative of x times the ln of x in respect to x is equal to uv. Don't be thrown off by how confusing that looks. It's not too, it doesn't end up being too hard in the end. Minus the integral of v du. And what happens here is now the integral of the v, of dv, so our x squared, and our derivative of the u can work together. X squared over 2 times 1 over x dx, those x's can cancel out a bit. X over 2 dx. And now I have something whose antiderivative I can take easily, so I'll be able to finish off this indefinite integral. The x squared ln of x is good the way it is, minus the antiderivative of x is x squared over 2, which becomes x squared over 4 because of that other 2 that's already down there, plus c. So now that I know the antiderivative of x ln of x dx, I can go back to the original problem, which was a definite integral, and say the definite integral from 2 to 4 of x ln of x in respect to x, using the fundamental theorem, is the antiderivative of that integrand. So that is x squared ln of x over 2 minus x squared over 4. I don't need the plus c. Evaluated from 2 to 4. So the strategy here is different from before. What I'm going to recommend you do is first find the antiderivative, the indefinite integral, and then apply it to the fundamental theorem. So this equals 4 squared times the ln of 4 over 2 minus 4 squared over 4 minus, and remember when we're doing the fundamental theorem, remember be careful about this parentheses that's here because I'm going to have to distribute that negative. 2 squared ln of 2 over 2 minus 2 squared over 4. And so that equals 8 ln of 4 minus 4, although this minus 4 I'm about to add 1 to it, so I'll just call it minus 3. Remember, I'm adding 1 because of the double negatives. Minus 2 ln of 2. And you know what? You can call it a day there. You've simplified, or at least you've evaluated. You can simplify the ln of 4 and the ln of 2, although it looks like they can't combine them. If you remember our properties of logs, the ln of 4 is really 2 times the ln of 2, because 4 is 2 squared, and we have a power property that lets us bring that exponent down. So I can rewrite that as 16 ln of 2 minus 3 minus 2 ln of 2. And the only reason to do that is because now I can combine my ln's of 2. And that would be your answer. 14 ln of 2 minus 3. I will show you one other way to look at this, and something which occasionally you'll see. If you don't like the idea of finding the indefinite integral on the side and then applying the limits of integration, one thing you can do is do the same thing with our definite integral, with our integration by parts. Our u is the ln of x, our dv equals x dx, so du is 1 over x dx, and v is x squared over 2. And you can apply the limits of integration directly here if you want. I don't recommend doing this usually, but occasionally you'll see a multiple choice question that has an answer that looks something like this. So just to make sure you're aware of it when you see it, you might see the uv, which was x squared ln of x over 2, evaluated from the lower limit to the upper limit, minus the definite integral from the lower limit to the upper limit of v du. And then from there, you would proceed in exactly the same way we just did, evaluating this from 2 to 4. Well, we did that in our parentheses on the last page. And evaluating the definite integral would be first taking the antiderivative and then evaluating that from 2 to 4. It's not different from what we saw already. It's just a slightly different notation that I want you to be comfortable seeing. And eventually you lead to the same answer of 14 times the ln of 2 minus